Okay, so, well, with that, the last talk in the session is Christophe Clanet, who will talk about shapes in Olympic Games.
Yes, thank you, Mr. Sharman. Thank you, André, for the invitation to this colloquium, which has been very diverse and interesting so far. The idea is to talk about two types of shapes that we have observed in the lab, and one that will have to do with the shape of rowing boats, and the other one about the shape of divers and the cavity they produce while diving. So what we have at the moment in the lab is an activity around sports. So all of them are done in this sports group at École Polytechnique. And so the type of subject that we are studying at the moment are shooting, skiing, some rowing, some collective games, and the diving that I mentioned before. So the person in charge of those themes, so the one that are not here but who have done the job, Caroline Cohen for the shooting and the skiing, Tom Maddalena so he's doing his PhD on shooting subjects, Romain Labbé for the rowing, Vincent Bacot for the collective games, Jean-Philippe Boucher with Romain for the rowing, and Thibault for the diving. And since we are running for the 2024 Olympic Games, the number of subjects is going to increase. The one I want to mention, because I think it's one of the more difficult experiments that we have at the moment, is to produce a little ski station in Paris in order to study the friction on snow. And so this has been done by Caroline Cohen. So the idea was to buy a fridge, something like less than 10,000 euro on eBay, and then to produce the snow, our own snow, by let's say pulverizing water, and then put a ski and drag it. So the movie, and measure the friction in order to understand how wax. So the question is to understand how wax is, let's say, decreasing the friction on snow. And this experiment is done together with Lidéric Bocquet at École Normale, who is looking at the small scale interaction between a snow crystal and a solid surface. And the two experiments are needed because you have as mentioned for the ice, you have a small liquid layer. So we have measured 200 nanometers that produces the lowering of the friction and produces effect at the scale of the meter. But today the point is to discuss shape. This was the topic of the colloquium, and so I will focus on one of the studies that we have at the moment in the lab, which is on rowing. Since we are in Cambridge, I had to go through the boat race, who started in 1829. So this is a painting at the time. And this race is between two bridges, Putney Bridge and Chiswick Bridge, so just at the edge of London, let's say. And the race is going to go from Putney to Chiswick, which is against the current, right? Because the current is flowing towards the ocean. And so when you get the information about the race, so the people who row are called the blues, so light blue for Cambridge and dark blue for Oxford. And you know everything about the race, and you know the length of the race. So the length of the race is 6.8 kilometers, and you know the record of the race, and so you can deduce the maximum velocity during this record, which is 6.94 meters per second. And the surprise is to see that the Olympic record is 6.27. So they are running against the current and producing a velocity which is larger. So this is the first surprise. In fact, it's not a surprise because the race is synchronized with the tides. And so they run the race when the water comes into the channel. And so this is probably the reason, but I was surprised by this number. About the winning, so Cambridge has the lead for the moment, 82, and Oxford 80, so they are very close. And for the women it's the same, so for the women Cambridge is leading by far, by more than 10 victories. What more, there is one dead heat, so equality. At the time there was no bridge, and it seems that one of the race, only one over the 163, where they finished equal. They were not able to determine who, after almost 7 kilometers, won the race. Okay, so the question we are going to address in this talk has to do with velocity, shape, and about the best way of rowing. So we start with the velocity. So there are two types of rowing: school, where each rower has 2 oars, and sweeping, where each rower has only 1 oar. And the velocity increases with the number of rowers, but not a lot. So it goes from 5 meters per second up to 6.5 meters per second. This is for men. You have the same law for women. And this weak dependency of the velocity of the number of horsemen, yes, or horsewomen, I don't know how to say, has been proposed by McMahon to be power law, so that the velocity should go like the number of rowers to the 1/9, and this is the solid line which is plotted here. And so the idea is to try to understand this law. One remark is that rowing is the fastest sport compared to kayaking, for example. So here you have the point for kayak, and for canoeing. So this is the lower speed you get, but always the same evolution with the number of rowers. So if you go through the McMahon idea, so this is extracted from his original paper. So the length of the boat is called little l, the width is b. You have the evolution of the length with the number of rowers. So you see that changing, so moving from 1 rower to 8, the length of the boat changes from 8 meters to 18 meters. The ratio, so the aspect ratio of the boat, so the ratio between the length and the width, is of the order of let's say 25 plus or minus 20%. And this is the boat weight per horseman. The idea of McMahon are the following. So we will assume, based on this data, that there is a geometrical similarity. So there is only one length scale in the problem. So the volume of the boat will go like L cube. Since buoyancy has to compensate the weight of the boat, you expect the volume to go like the number of rowers. And already these two relationships tells you that the length should go like n to the power 1/3. And so moving from n equal 1 to n equal 8 to the 1/3, you expect the length of the boat to change by a factor of 2, right? And so here we observe that we're changing by a little bit more than a factor of 2, from 8, let's say, to 18. And it's not far. And so if you add to this the fact that the power of each rower time the number of rower will be the power that you will dedicate it to the propulsion of the boat, you compensate this propulsion by the friction, which at large Reynolds number will go like rho v squared times the weighted surface. To get a power, you multiply by v, so you get this relationship between the velocity and the power. We have observed that there is only one length scale, so BL is going to go like L square. L square is n to the 2/3, and so n to the 2/3 here, n to the 3/3 there. You expect v cube to go like n to the 1/3, right? And so this tells you that the velocity should indeed go like the number of rowers to the 1/9. So these are the idea of McMahon. What we are going to question is this relationship, right? This relationship, because if you go to a large number of rowers, so let's say here 24. So this is a boat done by the Swedes. It's called Stempfli Express. It's a rowing boat of 24 rowers. And the boat is 54 meters long, right?
Why?
So if you move from 1 to 24 to the power 1/3, this makes 2.88. And so you would expect the length of the boat to be 8 meters for 1 rower, times 24 to the 1/3, which would be 23 meters, right? And 23 meters is very different from 54, right? And so what you see here is that at one point 23 meters does not allow people to put their leg. So if you take a boat that goes like n to the 1/3, at one point you compress the people, right? And so this boat at the 20,001 World Championship in Lucerne, Switzerland, made an attempt to break the world record on 2,000 meters. However, the crew failed to beat the then record of 5 minutes 20 seconds, held by the Dutchman that were only 8. And so here we understand that there is a problem with McMahon, right? So we have multiplied by the number of rows by 3, and the velocity has decreased. At least they made it almost equal. And so what I was just mentioning is that if you what you want in the boat is to be able to put your leg in the boat, right? And so this tells you that the law that the similarity law that tells you that L will go like n to the 1/3, you can take it provided you can put your leg. If you cannot put your leg, then you move to another law where the length of the boat will be linear with the number of rowers in order for them to have the... If this is the second regime, which already starts for n equal 8, you see that 1/3 was very good for 1, 2, and 4. But for 8, you have a little slightly change here. Well, you can take the same law as McMahon, but now in the second regime, for the large the number of rowers, L is going to be like n in order to put the legs. And so this means that you will lose the length, the number of rower dependency, right? Because the other relation you have is that the surface times the length should be equal to the volume, and the volume is also proportional to n. And so if the length goes like n, you deduce that the section should be constant, and the section will be fixed by the size of the guy, right? And so the relation you expect is to have the velocity in the large number of rowers to be independent of n and to scale like this. And so this you can check. And about the velocity in rowing, there are 2 different regimes: the low number of rower, where the velocity will increase like n to the 1/9, and the large number of rower, where you expect a constant velocity. And in fact, this is kind of interesting in the sense that why did we stop the competition at 8? Well, probably because they have tested 16, and since the velocity did not increase, we have stopped the competition when the velocity was not changing anymore. So this is a guess. And you see that 8 is really at the transition. Right? Okay, so now we move to the shape, which is part 2 of the let's say the discussion today. And I will first start with a naive view on what makes the shape of a boat. The naive view goes as follows. So we have a volume that goes like the length times the width times the thickness of the boat. First, we have Archimedes relationship that says that the number of rowers will impose a volume. Then, so to design the boat, we work at a constant volume. We have a fixed volume. Second, we know that the friction force is proportional to the wetted surface. And so if you think about, for a given volume, minimizing the wetted surface, you end up with a sphere, right? But the problem with the sphere is that it will have detachment. And so what you really want is to lower the friction force, and the friction force is proportional to the wetted surface times a coefficient. And this coefficient depends on the flow that you have behind the shape, right? So if you have detachment, you will have a large drag coefficient. If you manage to increase a little bit the surface but prevent the detachment, then this will lower the friction coefficient. And so at the end, what you want is to lower the value of S times CD. And so you expect a shape like this to do a good job, right? And so this is why, for example, torpedo or the bulb of a ship, they have exactly this shape, which is a wing shape. But this is not this is not still a rowing boat, right? So we are missing something. So we test, we take this shape, and what we are going to do is to look at the drag of this shape when we move it either on the right direction, so in the blue direction where you are supposed to have a low drag, either on the opposite direction. And we will do this experiment for different depths, right? So we first look when the shape is below the interface. So you are below the interface, and in this case, if you move in the blue direction, so indeed the friction coefficient is lower than if you move to the red direction, right? So this is what you expect. You have designed the shape in order to have a lower friction coefficient when you move to the right. But if you move this shape at the interface, then things changes, and the one that goes to the red direction, to the left, has a lower friction than the one that moves to the right. And so this has to do with the wave that are produced, right? So you produce less wave at the interface when you have the sharp edge than if you move with the rounded one. And so at the end, the naive view is the following. So if you want to move a solid body at the interface, you have to pay attention to both wave and to detachment, right? And so the front part will be dedicated to the wave, and the bottom part to avoiding the detachment. And so then you couple to the two, and you get close to a rowing boat. Right? So obviously, you can do much better than this. This was, let's say, a naive view. And so the next step is to take this idea and to discuss the aspect ratio and the shape of the optimal shape of the boat. First, we observe that for all the creature that moves at the interface, you have several aspect ratio, and those aspect ratio vary with the Froude number. So there are lots of dispersion, but they vary with the Froude number, and they peak at a value of 30 for the rowing boat. So the problem we did was to simplify the geometry, take a symmetrical shape, and for this geometry define three dimensionless parameters. So the aspect ratio alpha, the ratio between the depth of immersion and the width that we call beta, and the Froude number, which is the non-dimensional velocity that characterizes the motion at the interface. And then the total force that we are going to minimize will be rho u square s times 2 coefficient of friction, one that takes into account the wave drag, so, and the other one which is skin friction. So the two things that we have seen important in order to make a boat. And so then this makes this relationship, so we have a force that will go like a rho u squared times a surface, time a coefficient that we want to minimize, and that is a function of the aspect ratio, of the depth to width ratio, and to the Froude number. When you do the minimization, you get this answer. So for a given depth to width ratio and a given Froude number, you have an optimum aspect ratio that gives you the lower friction coefficient. What you see is that the dependency on beta is not large, in the sense that you have almost a translation shape in the plane, and so this gives you that in fact the aspect ratio that you have observed for the moving boat at the interface, they verify they have been let's say designed in order to lower the friction and also to ensure stability. You see that here the lowering the interface, so these are for cruising boat. If you those should have an aspect ratio much larger, but since there are stability problem with large aspect ratio, they try to find a compromise. But for rowing, since you have a competition on the velocity, then you will manage with the stability, and you take the aspect ratio that minimizes the friction. Okay, what you can do is to let's say take the same result, and now for a given aspect ratio and a given Froude number, find the optimal beta. And so this will produce a second manifold, and the intersection between the two manifolds gives the black line. And so up to now we have only discussed the friction. We have not discussed the fact that the boat we are designing is propelled by men, right? And so if we put these constraints so that they have a constant power per rower, this gives us this complementary line. For one rower we have the blue, and so this tells us that as the number of rower is going to increase, the Froude number is going to decrease, right? And that the aspect ratio should increase, right? And so this is what we see here when the number of rowers increase, the full number decrease, and the aspect ratio does increase, right? And so this is one way to go further the magma model and to try to understand what is behind the data that we have observed on field. Yeah. The last part of the problem that I want to discuss is on the best way of rowing. So if you look at the competition, you see that all the rowers move at the same time. So they use a synchronized way of rowing. And this has an impact on the velocity, obviously. So if you look at the velocity of the boat as a function of time, you get this type of oscillation. And you see that you have a oscillation of, so the velocity changes from 4 to 7 meters per second, so you have 30% of variation. And this is a surprise in the sense that the friction, so the energy you spend per unit of time, depends on the mean velocity, and there is a penalty on the oscillation. So you wonder, why do they produce such a way, right? You would expect that something that would be smoother should spend less energy. And so this was the initial idea. And the idea was, let's say, push further, because in nature nobody uses a synchronized way of actioning the legs. There is always a wave propagating from head to tail that moves here the shrimp at a constant velocity. You don't see lots of fluctuation in the shrimp, right? And so what we did was, so what Romain and Jean-Philippe did was to design a robot, a rowing robot, so a rowboat, and in order to test this idea of synchronization. And so the first, so the train will, so the first case is our.
The stabilizer.
Yeah, this illustrates the fact that they are not stable, right? There's no. And in the first case, then you do reproduce the oscillation that you observe on real competition, and then you desynchronize the rowers. So you take 2 pi divided by 8 in order that after one cycle the wave has moved along the whole boat. And in this case the fluctuation has been divided by 10, right? So the motion is much smoother. But it's also slower. So here you have the evolution of the mean velocity of the boat as a function of the phase. So the maximum velocity is achieved for 0 phase difference c. And so the point is that we are missing something. And what we are missing is the following. So here I have put in purple the duration, the period during which the oars are inside the water. So here the oars enter the water, here the oars go out of the water. And so without any surprise, when the oars are in the water, the velocity increased, which means that there is an acceleration, and so a force acting on the boat, which is what you expect. But the surprise is that you also observe that the velocity still increases when the oars are out of the water, right? And so this is related to the fact that the horsemen or horsewomen are moving at the surface of the boat, right? And so there is in rowing, and this is different from canoe, for example, there is a propulsion by related to the oars, and there is an inertial propulsion. And so when you desynchronize the boat, you are losing this one, which is not ridiculous, right? It's 1/3 of the total thing. And so for sure you are decreasing the friction, but you are also decreasing the propulsion. And so this is the. And so what has been designed by Romain and Jean-Philippe to show this idea is a boat without oars. So only a mass which is moving back and forth. And here you have 2 things that enters the water or goes out, but without being active. So they are here just to change the drag coefficient in, depending on the direction, right? Which is what you have also in rowing, because when the rowers are moving, in one part of the motion the oars are out, and in the other part they are in, right? So you expect a change of drag coefficient between the 2 ways of moving. Okay, how many times do I have?
15 minutes.
15 minutes? Oh, plenty.
10 plus 5. Plenty of time.
Plenty of time. So then you can put this into equation and you recover the good dependency. And so what is done at the moment with Thomas Baruch is to look how to use this understanding that we have of the propulsion in order to maximize the velocity. Because if you put the oars in the water and then move your body just afterwards. So you will for sure have the two propulsion means, but you will also have the maximum amplitude of the oscillation. And so if you delay a little bit the two phases, right? So if you let the friction act during a small delay, so you will still be able to use the two propulsion forces, but to lower a little bit the oscillation, right? So at the moment there is no delay, so there is no resting phase between the two phases, and so this produces maximum oscillation and so maximum drag force. The idea is to try to introduce a small delay and to see if this helps or not. Okay. So the second part is dedicated to diving. So here you recognize the diving of a man. There are the feet here. So man or woman, but at least he's a human, right? And the subject is treated with Thibaut Guillet, and the champion with whom we work is David Colterie, and he contacted us. So he's an athlete followed by Red Bull, and they have problem of adductor injury as they enter the water. So because the water want to spread the legs apart, and so this is a big, let's say, effect or injuries, and so they want to see what can we do to avoid this. So first I present what they are type of competition they are involved in.
Locals call this spot the Serpent's Lair on the Isle of Innismore in Ireland, where gale force winds can scream over icy waters. Only the most intrepid dare it all for that perfect dive. David Curry is one of them.
A little bit over on the entry, but all in all, first time, so that's always the most nerve-wracking.
This is the Red Bull Cliff Diving World Series. 22 athletes, 6 events, and only one way out. A 90-foot plunge into frigid darkness.
Okay.
90 feet.
So it's 28 meters for men and 21 for women.
You have to have the feet in first. The regular diving has the head in.
Yeah. So this is the first point. So you can enter the water with head first up to 15 meters. After that, the arms they go spread apart and you injure yourself. And so all of them systematically above 15 meters they enter feet first, right? So I'm going to play this movie twice. So this is a movie that he sent us to show the initial phase of the water entry, right? And so what I want you to observe is that this first phase, so the initial phase of the water entry is not exactly straight, right? And I will come back on that. So please observe this. So can we help you? Up, there is a little zigzag there, right?
The impact is just immense. You can feel like an uppercut from one side.
You hit the water and it's a total shockwave through your whole body.
Okay, I think these are gannets. Gannets, les fous de bassin. So gannets, yeah. And so they dive. So what we know about gannets is that they dive from 30 meters, no more. And they hit the water at the same speed as human, which is of the order of 90 kilometers per hour. Right? You see these,
90 kilometers per hour.
And so what we did in order to understand this problem is to look at the impact of slender bodies. And so at low velocity there is a straight path. If you increase the velocity, you start to see a little bit what we saw in the movie, which is a little zigzag. If you still increase the velocity, and so this is a very special object in the sense that the evolution of the diving depth as a function of the velocity is not monotonous. So there is a height for which the diving depth is maximized, right, which is very different from a sphere, for example.
This is spontaneous symmetry breaking?
Yes, spontaneous symmetry breaking. And so the idea is to give you a flavor of the origin of the symmetry breaking, and then also to discuss the maximum depth, right? Because you imagine that if you want to fish, to get, let's say, you would like to maximize the diving depth, right? And if you can both maximize the diving depth and lower the impact velocity to avoid breaking your neck, this is a good solution, right? So the garnet will like to be in this regime. In the case of the diving man or woman, they would like to avoid to go too far deep in order to avoid reaching the soil and breaking their leg, right? So they all dive in 5 meters. So in order to produce the Red Bull competition, what they ask is to have 5 meter depth of water. If they have less than 5, they don't jump, and if they have more, they are happy, right? But they know that 5 meters is good to stop. And so the diving man or woman would like to be here, and the garnet would like to be there. Okay, so the origin of the symmetry breaking is the fact that you have the center of gravity, which is at a different place to 2 different points. So the one which is the place where buoyancy acts, so the geometrical center of the body, and the one where the aerodynamical lift applies. And so this one does not exist when you are at rest, let's say, right? So at rest you have only an equilibrium which is fixed by the weight and Archimedia. As soon as there is a velocity, this one will apply, and the location of application of the aerodynamical force will depend on the angle alpha, right? But at small angle alpha, which is the initial limit, the application point is very close to the nose, right? So something like 5% of the total thing. So if this is 0%, 100%, the location we have measured is 5% at small alpha. And so if L wins, so at large velocity, you expect the torque, destabilizing torque, to win, and if L is low, which is at low velocity, you expect the stabilizing torque produced by gravity to win. So this is what we have looked for. So there is a transition speed for which you expect to move from stable to unstable. What I have in these 2 axes is the position of the gravitational center, so the application where the point where the weight applied, and for a given shape I know that there is a geometrical center where the buoyancy will apply, but I can move G, right, along the shape. I can move it from 0 to 1. So this is in percent of the chord, so I can move it from 0 to 100%. And so at low velocity, so that I will have no solicitation of the lift force, or a weak one, so I will be in the stable regime, and as I increase the velocity I will move to the unstable one. The line here tells me that I have a small uncertainty on the initial angle of impact, right? So I don't know exactly. I don't know if it's I know it's below 4 degrees, but I don't know if it's 1 or 4 degrees, and so I have a little uncertainty about the transition. And so we made the experiment for in the different zones here, and initially, so at low velocity, and when the position of the center of DG, let's say, is smaller than 35 degrees, I am in a stable regime, and I have almost a straight trajectory. When I move in the other regime, then I have either, by increasing the velocity, the S shape that I have produced, either when the 2 forces, so when I have moved my center of gravity further back, then the 2 forces act in the same direction, which is in the destabilizing thing, and I have loops like this, right? And so these are the different regimes that we can have in this experiment. I come back now to the non-monotonous evolution of the penetration depth. So the idea is to try to understand why could we have a maximum, and in order to discuss this point, what we do is to take a drag coefficient which is let's say expected at large Reynolds number, and we make it work over the penetration depth L, and we know that this work has to compensate the initial kinetic energy, Yeah, 5 minutes. I will be done. So these relationships tells you that if you are interested in the evolution of L as a function of u, the L du should go like a prefactor and should be sensitive to the variation of the drag coefficient with the velocity. And then the only thing you have to do is to plot the penetration depth as the velocity. You separate the two sides, so one that does not produce cavity at low velocity and the one that does produce cavity at large velocity. If you don't have any cavity, you will have a slender body, so you will have a drag coefficient that will go like 1 over the square root of the Reynolds number if there is no transition to turbulence. And if there is cavity, then the flow doesn't know if the object is slender or bluff, right? There is a cavity, so it will appear as a bluff body, so you expect a constant drag coefficient here. And that's it, right? Because in the first phase, since you have the drag coefficient that goes like 1 over the square root of u, dCd du is going to impose a negative value of this, and so you expect the L du to be positive. And so the penetration depth should increase with the velocity up to the creation of the cavity. The second thing that you know is that the drag on a slender body is lower than the drag on a bluff body, and so when you are going to cross this border, dCd du is going to increase. Right? You don't know how, but it's going to increase. If this one is positive, this means that dL du is negative, and so you expect something like this. Right? And when you reach the regime where CD becomes constant, then dCd du is 0, and so you expect this. Right? And so here you have the non-monotonous, at least a sketch of the origin of the non-monotonous behavior of the penetration depth with the Gannet regimes. So the Gannet, they are at the edge, right? So you can dive, you can have a large penetration depth at a low velocity of impact, let's say low, still 90 kilometers per hour. And here you have the regime of the divers, where you want to stop your body quickly in order to avoid reaching the bottom. Okay, and with this I would like to thank you, and
we have time for a question or two.
Yeah. You had this graph showing that above 8 you sort of leveled off, but I wasn't sure. Is that real data, or is that from a simulation?
I think there is non-simulation in the talk, so it has to be experiment, right?
Okay.
You are speaking about this
No,
one,
no,
right?
the one with the red curve.
This is what you are referring to, right?
No.
We're talking about the last graph.
Yeah, I think so.
That was scaling sort of analysis showing the general shape of what you would expect, and previously he showed data that follow that trend.
So I guess one issue is I can think of lots of reasons why 54
This
person.
one?
No, for the rowing.
Sorry, I think I don't understand the graph you are referring to.
No, it's fine.
So it's about rowing, and it's about which question? Is it on the velocity?
So it's the.
We can move. So these are real data.
Yeah. So it's when you get to this sort of 54, this mega rowing boat. Yeah. So and then after this, you show this graph where. No, I think keep going. Is there another one after this? Oh yeah, no. So it was that one. Yeah, it's the right-hand side. I see. Yeah, my mistake. Yeah. So the dots on that right-hand
So
side.
these are the points that you can that you have. So these are the Olympic records. So
Yeah.
the first 4, and this is the one achieved by the 24 people boat.
Okay, so I can think of many other reasons why that wouldn't work so well. For example, maybe they didn't have much time to train on such an exceptional boat, and a team of 8, you get to select your 8 best rowers from, say, 54, but with 54, 24, but with 24, you, by necessity, have to take weaker rowers. So I just wonder if there are other reasons that might explain this.
In fact, I think the answer is here, right? They constructed, so these people, they have constructed this boat to break the world record. So I guess that they didn't put someone of 70 years old rowing. So I think they took people that were able to break the record. Because you're not going to construct a boat like this, because this is going to cost some money, and we are in Switzerland, right? So I would think that in France we could do something that costs money and doesn't work. We are able to do this, but in Switzerland, if they put money, they want result, right? So I guess that they took people able to break the record. So I would not follow this path.
Well, I don't know. For the other records, people have had multiple attempts. Here it's like a single attempt. So
Oh no! Yeah, it was one single here, but then they did it again, right? I mean, I guess that they practiced before the World Championship, but this is true that they put the pressure on the rowers during the World Championship.
Okay, I still think there's hope for the stamp fleet. I think it can do it.
Train. But you can test this in your robot to some extent, right?
You can do the robot stamp fleet.
Yeah. I can try to break the record.
Yes, Steve.
The most famous rowboats in history are Greek triremes,
Yeah.
which had 300 rowers
No,
or something like that.
170.
Okay, but they're huge, and
Yeah.
they have 3 rows of rowers.
Yeah, 3 rows. Yeah.
They presumably optimized those after battling the Phoenicians for a few decades. So
Yeah, the velocity record that you find for them is of the order. So here it's 6 meters per second for the triad. The Greek triad is is between 5 and 6. So we don't have exactly the numbers, but for 170 rowers. So the boat was a little bit different, right? The aspect ratio is not 30 and so on. So it was not optimized for lowering the drag, because when you put, but this is okay. I think that there is one question that we did not answer, and that is for me very, let's say, interesting in the sense that if you increase the number of rowers, what you see is that below a first critical number, you put the rowers along a line, right? Above a critical number, then you put them on a surface. So you have 2 lines of rowers, and then there is another transition where you put them on a volume, one over the other. So the triad. So the 170 rowers is for sure in the regime where you put them along a volume. But understanding this transition from a line that is going to a walk and produce a surface, and the surface is going to a walk and go produce a volume. I mean, this is a very nice question, but I don't have the answer for this one.
So one thing they talk about that having a longboat has to do the wave speed, and that goes square root of L, and I don't know if that's taken into account. So that would argue for a longer boat.
Yeah. So in fact what we see, so this is the point here, is that rowing your fruit 0.5, no matter. So so you have this is
0.5 fruit number.
So this is rowing and this is kayaking. Right.
Okay. So it is, you do have that.
Yeah.
What is the star?
So the star is this one, where you have 2.
Something of that.
If you could avoid the fluctuation in velocity, is there one regime where you could think that foils become efficient?
Oh yeah. Foils. So the point is that you have to design foils where with rowing are able to move you out of the water. But yes, so for the moment they are not allowed in competition, but you start to see foils on rowing boats. Yeah. And then you will be able to increase the velocity for sure.
they are allowed in sailboat racing.
Yeah, they are allowed in sailboat.
The America's Cup has foils all over the place now.
Yeah, but with rowing, the change in velocity is no good for...
One last question, or 2 last questions, and then we'll close up.
And what you can say about the optimal shape of the cross-section and the nose of the boat?
Yeah, nothing for the moment. No, but the nose of the boat is a very important point, especially for the wave production. But so it's something that is on our list, but I cannot say anything.
Maybe gets the last.
So I have two questions about the oars. And one is, what's the difference between one guy with two and then alternating in terms of how fast they go? And then also, have you looked at the length of the oars?
Yeah, so the oars is a hot topic for us because, for example, what is hot in the case of oars is it has to couple with the physiology of the people. And so when you discuss elasticity of the oars, when you discuss the surface of the oars, then you cannot forget then the oars are going to be used by a man or a woman. And so then there is a coupling with the physiology, which makes the problem very interesting, but much more complicated than the one of the shape of the hull. Right? And so we are indeed working on this. So the first thing that we did was to put elasticity and to try to see if we can increase the propulsion force using elasticity, and the answer is no, because one part of the main part of the propulsion comes from the added mass part. And for this you need an acceleration which is as large as possible, which is the stiffest the oars, the better, right? So when you discuss with the athletes, at the moment they have three types of elasticity: low elasticity, medium, and large. And they say, since we don't know the effect, we all take medium. So this is the. But the point is that we have the feeling that if you take them too stiff, then it's hurt your articulation. And so one way to understand that they take medium is that it's a way to train yourself every day, right, without injuring your body too much. But as far as physics is concerned, the stiffer the better for the propulsion.
And then the one oar or two oars per person?
Yeah, so in fact they don't have the same geometrical characteristics. So what we see is that the 2 oars per person goes faster by a small amount, but goes faster systematically, whatever the number of person and whatever the rower. But since they have different length, right, so both the length and the blade don't have the same surface, and so when we put the characteristic in our code, then we see that we have more propulsion force with 2 oars, even if they are smaller, than with one large.
To that question, the angle of attack of the, I noticed in your video of the Olympic guy, the paddle is basically, it's not perpendicular, it's...
No, because in fact what you want to enter is to enter at the same velocity as the water. You don't want to, this is something which was different between our robot. So they work a lot, because when you see, there is something that I did not perhaps underline here. So here, when you see something like this with the oars entering the water without decelerating the boat, this means that those people, they are trained, right? Because for our rowing boat, when they enter the water, so this is something that I didn't underline when we move to the rowing boat. Oh, here. So here when we enter the water, there is a deceleration. Right, and say this does not exist with high-level athletes.
So the Olympic guy that you showed,
yeah,
so that's why he's angling when
they
he comes
enter
in.
and already they accelerate.
So they flip the oar within the water.
While within the water.
Can you play his video again? Do you know which one I'm talking about? The single guy.
The bronze medalist.
The bronze medalist.
Oh.
The Rio, the bronze medalist.
Yes.
So this is
the angle.
So he digs in at an angle.
And the trick is to avoid decelerating the boat each time you enter. Yeah.
So when you start, you'd be vertical. When you're not yet.
Right.
Okay, many thanks.
Okay, fantastic. Let's thank Christophe again.